Hi, I'm Junkyu from AI Planning Group at IBM Research. This presentation introduces AI planning annotation in reinforcement learning, which is a kind of integrated method of AI planning and reinforcement learning for solving sequential decision-making problems. When solving sequential decision-making problems, AI planning and reinforcement learning approach both have its own strengths and weaknesses. The integrated method aims to complement each other. Here we review the basic concepts and notations. We assume a discounted Markov decision process with finite set of states and actions. The solution to the problem is a stationary stochastic policy, which we can obtain by solving for the maximum expected utility. It's well known that the expected utility value function, given some policy function, or the optimal value function, can be written in recursive form, also known as Bellman equation. Graphically, we can visualize the MVP by the following graphical model. Option frameworks allows formulating the RL as a hierarchical RL by introducing options, where each option defines an MDP or SMDP with its own initiation set, termination set, and the intra-option policy function. In the following example, given an MDP, we generate actions through an additional random variable at each time step, denoted by O, where we first check which option can be initiated at each state, and then generate an action by the intra-option policy function. In the following stages, we check if the option selected at the previous stage can be terminated. If we can terminate that option, then we select a new option that can be initiated. Otherwise, we continue generating actions from the same intra-policy function. Here, the solution is the option level policy function that selects option at each stage, and a set of intra-option policy function, one per each option. The option level MDP is a semi-MDP since the duration of the option execution is now a random variable. The following example shows a case where the option O1 was selected at time step 0 and terminated at time step 3. Then option O5 was selected at time step 3 and then terminated at time step 4. By introducing option reward functions as a discounted sum of rewards that are accumulated during the option execution, we can express the value function for the semi-MDP over the options, similar to the value function for the flat MDP. Now we introduce a notation for a planning task. We have a set of finite domain variables and operators called states. A set of planning states, denoted by S prime, is a collection of symbolic planning state which is a full assignment to the variable. On the right, we show an example of action schema for the room navigation domain. Now we introduce planning annotated reinforcement learning task. It is a tuple of an MDP for reinforcement learning M, a planning task T, and the state mapping function L between the state spaces of the MDP and the AA planning task. Here we assume that the AA planning task provides some useful information about the underlying MDP model. The symbolic planning state is obtained by the state mapping function that essentially aggregates the RL states. Given an MDP, we define an option from each action operator in the AI planning task, where the initiation set is obtained by the precondition of the action operator, and the termination set is obtained by the effects. In the room navigation domain, if we had an action operator for moving from room 5 to a corridor between room 5 and room 3, we can test for the initiation or termination set by using the expression in the planning states through the state mapping function. In this way, we can define hierarchical RL with options defined by the PARL, except for the intra-option policy functions. For solving PARL, we can use both reinforcement learning and planning algorithms. For the room navigation domain, at the higher level, we see the symbolic planning states at the level of movements between the rooms. In this case, from room 1 to the room 2. If we treat this as a symbolic planning problem, the first action in the plan declares the agent to stay at the corridor between room and room 2, and then the second action declares the agent to reach the second room. Of course, the actual environment is not a deterministic planning problem, and This option sequence only guides what options to choose at each stage to the agent. As we can see, the PARL provides the side information to the RL agent so that we can use AI planning model for model-based HRL. When solving the task using PRL, we can think of two approaches. The first one is offline planning, where we pre-train all intra-option policy functions in advance before solving the SMDP. The other one is online planning, where we learn all policy functions during exploration. In this presentation, we show the offline approach. In many of the options framework, option discovery as well as option selection is an important problem as well as a difficult problem because there may be large number of options available to train and use. For this purpose, we can use the plan generated from a planner to select useful options. After identifying useful options, we can train them by using any reinforcement learning algorithm. Next, we train option level policy function based on SMDP learning, where the option level policy function can take the selected option or primitive actions as its action space. As a representative example, for 20 by 20 grid, 8-room navigation problem, we can see that the SMDP learning with the options derived from the PARL improves the sample efficiency compared with the flat RL approach, where we fixed reinforcement learning algorithm to the same PPO here. We introduced the planning annotated reinforcement learning task and showed how to define hierarchical reinforcement learning architecture by using AI planning task. For intra-option policy function training, we can use any reinforcement learning algorithm. For option level policy learning, we can utilize AI planning algorithm to improve the sample efficiency. Note that there is no strict requirements on the AI planning task. In addition, if a model was available for the reinforcement learning problem, then we can also utilize state abstraction method in AI planning to drive annotating planning task. As future work, we are working on online approach and algorithms for running AI planning tasks from the reinforcement learning environment. Thanks very much.